Hello everyone, welcome back. In today's session we are going to study about the combinational logic gates. Now we have studied about the inverter and the NAND gate using the CMOS. So these are the examples of complementary CMOS logic gates, which are also called as a static CMOS gates. Now in general, the full complementary CMOS gate has an NMOS pull down network to connect to the output 0, that is to the output of 0, and PMOS pull up network to connect to the output of 1, that is VDD. Now we can see here in this picture. In general, this is how the CMOS static gates looks. This is the PMOS pull up network, which is also called as PUN, and this is NMOS. So this is pull down network, that is PDN. And here we have input and this is the output. So this is the basic diagram of how it looks. Now the next work, now the networks are arranged such that one is on and the other is off for any input pattern. So how do we get the output through these networks is that by arranging it in parallel or in series network. So the pull up and pull down networks in the inverter each consisted of a single transistor. So we have seen that in inverter there was one single PMOS and there was one single NMOS transistor, and in NAND gate it used a series pull down network, means it used a series of NMOS network and parallel pull up network, that is a parallel PMOS network. More elaborate networks are used for more complex gates. So these were the combination for the NOT gate and the NAND gate. Now other combinations are also used for the more complex gates. Two or more transistors in series are on only if the series transistors are on, and two or more transistors in parallel are on if any of the parallel transistors are on. So this is illustrated here. Now from figure 1.14, for NMOS and PMOS transistor pairs, by using combination of these constructions, CMOS combinational gate can be constructed. So we know that basically CMOS is the combination of PMOS and NMOS. Now we can see how these combination, when arranged in different ways, give us the output. So this first diagram, we can see these two gates are there. So these two NMOS gates which are connected in series. Now when both are in series, what happens is that if both are on, then only we get the output as on. Now in first condition 0, 0, both are off, the output is off. Second condition 0, 1, only one is connected and one is not connected, so it is off. Again the next one is connected, one is not connected, it is off. Only when both are connected we get the output as on, when the NMOS are connected in series. Now coming to the next, again PMOS are connected in series. Now when PMOS are connected in series, when we have 0, 0 as input, then we get as on, because what happens is PMOS gives us a complementary output, that when the input is 0, it gives us the output as 1. So that is why when both the inputs are 0, 0 for PMOS, we get the output as on. And again, as it is in series, when one is closed and one is open, it will give off. Here also one is open, one is closed, it will give off. And again here, when it is 1, 1, that means both are open. For PMOS, when 1, 1 is there, both are open, it will give off. For NMOS, what happens when both are 1, 1, it will be connected and it will give the output as VDD. While for PMOS, when 1, 1 is given, it will be connected to the ground and it will give the output as 0. Now what is the next condition? For next combination, we have taken two NMOS which are in parallel. Now when two NMOS are in parallel, for a condition for parallel is that when one of it is connected, it will give us the on condition. Now here we see 0, 0, it is off, output is off, that is 0. When one is connected and one is open, it will give on. Again one is connected, 1 is open, it will give condition on, and for 1 again it will be on. So even if at least one of them is on and two are on, we get the on as output when the gates are connected in the parallel way. Now coming to the PMOS parallel combination. Now when PMOS are connected in parallel, what will happen is that when 0 0 is given, it will be connected and it will give on, and only when 1 is there, condition 1 is given as the input to the AB, it will give off, while for all other it will give us the on condition. Now in general, when we join a pull-up network to the pull-down network to form a logic gate as shown in figure 1.13, they both will attempt to exert a logic level at the output. The possible levels at the output are shown in table 1.3. From this table, it can be seen that the output of CMOS logic gate can be of 4 states. Now coming Now this is the table 1.3. So the 1 and 0 levels have been encountered with the inverter and NAND gates where either the pull-up or pull-down network is off. And the other structure is on. When the pull-up network and pull-down network are off, the high impedance or floating Z output results. And this is of importance in multipliers, memory elements and the bus drivers. The crow-borrowed X level exists between both pull-up and pull-down network are simultaneously turned on. This causes an indeterminate level and also static power to be dissipated. So these are the output states for the logic gate. Now pull down, so this is pull up, here pull up on and off condition, and here pull down on and off condition. So when pull down is off and pull up is also off, what happens is that Z, that is the high impedance condition, is satisfied. For the next one, pull down, that is NMOS are off and pull up is on. So when pull up is on, what happens is that we get it connected to VDD, so that is why the output will be 1. Now coming to the next condition, pull down will be on and pull up will be off. So it will be connected to VDD, so that is why we get the 0 as the output. And when both are on, say suppose in condition pull down is on and pull up is also on, it is crow-barred. And when pull down, so when both are off, it is high impedance. When both are on, it is crow-barred. Now coming to the NOR gate. So a 2-input NOR gate is shown in figure. The NMOS transistor are in parallel to the pull-out low when either input is high. The PMOS transistor are in series to pull the output high when both the inputs are low. So here we can see the diagram of NOR gate. Here NOR gate, it is shown that PMOS are connected in series while NMOS are connected in parallel. It is opposite to that of NAND gate where PMOS were in series and PMOS were in parallel and NMOS were in series, and here it is PMOS are in series and NMOS are in parallel. Now what happens here is when A is 0 and B is 0 for NOR gate. So what is NOR gate? NOR gate is opposite to that of OR gate. So what will be the condition? When the NOR gate will give us high, NOR gate will give us high only when A and B, that is both will be off. That is the condition where NOR gate will give us on condition. So what happens here is that the PMOS transistor are in series to pull the output high. So these are in series, which will give us the high output, and these are in parallel to which will give us the low output. And this is the symbol for NOR gate.